Thanks for the introduction. And hello, everyone. I'm Xingyu Wang from Northwestern University. So first, thanks for having me. And throughout the months, I've been interacting and learning from everyone. And I really appreciate this chance to learn from everyone and also this chance to present our own work. So the talk will be based on the joint work with Xingyu Wang and my advisor, Changhan Ri. And as you can see from the title, the topic will be about how we can use how we can understand and control the global dynamics of SGD using heavy tail noises. And for some of you, especially those that are here since the first week, you will find that this will have a lot of overlapping content with Changhan's tutorial. So please bear with me. And for those who still remember the content of the first week's tutorial, you probably remember that we start from an overview of what's going to happen under the truncated heavy tail noise in deep learning, and then a more detailed analysis and introduction of the machinery for us to obtain the results. So the purpose of this talk today here is to try to find the midpoint that we're trying to kind of compress everything into the talk and give everyone an overview of what will happen in deep learning under heavy tail noises and what are the tools necessary for us to understand these phenomena. All right, so that's the goal here. I hope still everyone could find something interesting from the talk. And yeah, let's get started. Well, we'll start by maybe introducing not the right word because everyone's familiar with this, but we will start by talking about the generalization mystery. So of course, in 2024, when we talk about deep neural nets, we are thinking about these models with potentially trillions of parameters, and they can potentially say very efficiently and accurately detect objects from visual informations. They can say accurately predict the words from a very long sentences or paragraphs, and they can actually translate the complicated description of text into a very vivid and lively, realistic images. But behind these empirical success, there's still a fundamental mystery that is how we can train these complicated models and make them generalized to the unseen settings. To be slightly more specific, this is what we meant. So when we train these deep neural nets, we will of course use the available training data. But the ultimate goal is that we hope this model will generalize to the unseen setting. And when we and despite their simplicity, the first order methods such as SGD and their variants have been doing pretty well in terms of the generalization performance, but the reason still largely remains a mystery. In fact, if we frame the training process as a non-convex optimization problem, then the question is how we can navigate through these highly complicated loss landscape, and how amongst the numerous local minima, why we are able to find the ones that actually generalize better. Regarding this generalization mystery, a popular belief or a folklore that has been gaining a lot of momentum recently is that the geometry of the solution plays a vital role. More specifically, the flatter the minima is, the better they tend to generalize in the test setting. So this is a hypothesis or thinking that goes back to 2 or 3 decades earlier, and it get popular again recently by Jorge Nocer and the other students in his group. So he's a professor in our department at Northwestern IEMS. Here's which started I think an active and still ongoing analysis and debate about why we have this phenomenon. Here, I'm just trying to provide a visual explanation at an intuitive level. And this is just one of the explanations why this may hold. So let's say the dashed black line is illustrating the population loss function, which we may not have access to. In the actual training, we will have a certain amount of training data, which gives us a training loss function. Suppose that it's a slightly perturbed version of the population loss, then we denote the training function as f. Then if we stay somewhere sharp, then once we switch from the training to the test setting, we can see that we're subject to a pretty large perturbation, which will lead to a rapid change in the output and performance of the model. In comparison, if you stay somewhere flat, then when switching from the training to the test setting, you're subject to a much smaller perturbation, which implies a much more robust performance and hence a better performance in the test setting. So this is at least one of the intuitive explanation for this phenomenon. And as I said, there have been a lot of research on this front and have been a lot of, I would say, exciting empirical and theoretical results. In general, I would say there are more and more empirical evidences. Some are actually from the pretty large scale studies that at least by trying to go somewhere flatter, you tend to achieve better performance in a variety of tasks. So in summary, there are a lot of research already regarding this flat minima mystery, and also a lot of empirical evidences supporting the hypothesis. But this is still far from the end of the story because for our purpose, which we're analyzing the generalized performance of SGD, even if we say for now, assume that in many or most cases, it's better to stay at a flatter region. The real question is how do we manage to get there? In particular, how the randomness, the noises in SGD can drive you to explore the landscape and manage to find the flatter, better regions. So the goal of this talk is to show that there is a way to provide an almost always guarantee that we can stay at the flat minimum. Yeah, so this will be the goal of this talk. And the reason we can achieve this is by understanding the role of the heavy tail noise in the training dynamics. Here we will make things more specific. So let's use F to denote the training loss function. And we use eta to denote the step lengths. In other words, the learning rate. The difference between the deterministic gradient descent iterates and its stochastic counterpart is that in SGD, for each iteration, you will be subject to some random perturbations. The standard, the more conventional standard assumption is that these random perturbations are light-out, say they follow. In some work, you assume that they follow the Gaussian type distributions. In some work, you just assume that it's from a finite system. They actually have a bounded support. But in this talk, we take a different perspective. That is, we assume that they're heavy tail. More precisely, we assume they are regularly varying noises. But the point is that now the extreme values are much more frequent. So throughout this month, and especially the past few days, we have seen a lot of exciting talks about heavy tail SGD. So I'm sure I don't need to provide more motivations to convince you guys that this is an interesting topic. But generally speaking, there are at least some observations, at least the existing results can fall into these field categories, especially those that are more related to the current work. So first, there are, in terms of regarding heavy tail in SGD or in machine learning in general, there are works studying how heavy tail noise arise in the gradient noise in different tasks. Also, as we have seen from Wu and Mer's talk, it seems like heavy tail phenomena can arise naturally in the stationary distribution of the training dynamics, even if all moving components, even in a case where it seems like all the moving components of the training dynamics are light. And more generally speaking, we have seen this throughout the months. That is, heavy tail might play a role, especially they may provide a benefit in achieving better generalization performance. More specifically, or on a more related note to this talk, there are work showing that it seems like heavy tail dynamics prefer flat minima. So this is what I mean. So let's suppose we are exploring a loss landscape like this that has the two sharper regions on the left and right boundary and the flatter region in the middle. What has been shown is that under the right asymptotic regimes, asymptotically, when the training dynamics driven by heavy tail noises, they tend to spend more time in the middle compared to the sharper regions. So this at least provides a partial explanation and a connection between the heavy tail noise and the better generalization performance. So these are, in summary, these are all existing and exciting results and insights. What's still missing here, though, is that there's still a gap between what has been understood and what's actually happening in practice. In particular, when we are training, let's say we're training deep neural nets for a certain task, and you observe that these gradient noise, these perturbations are actually more extreme than you think, then in many cases, you will try to control these noises. Otherwise, it's going to be even hard for the model to converge. And in many cases, the standard approach is that we're going to truncate these heavy numbers, which leads to the question that after truncation, is it still going to prefer flat minima? Or more specifically, what even is a truncated habitat noise in these tasks? So yeah, this is what we're trying to understand. Let's make this more specifically, especially about what I meant by truncation in the habitat noise. So I'm just referring to the, again, eta is a step length. I'm just referring to the standard gradient clipping operator. So B will be a clipping threshold. What the operator does is it takes the stochastic gradient, it keeps the direction, but rescales it if the distance, if the length norm exceeds the threshold B. Basically, it guarantees that the distance we're traveling at each step is bounded by the threshold B. So with each iteration, we're always moving within a bounded region. For the purpose of generalization, or at least exploring of the loss landscape, if you think about it, at least at first glance, this might be counterintuitive because if we believe that this more intense noise can help you at least explore the landscape in a more efficient manner, then after you truncate it, you actually remove any potential heavy tone in the noises. And you're providing a movement within a bounded region. So at least at first glance, it's unclear if this is a good idea for better generalization. So this question, we have the following simulation experiment, which is kind of a trailer of the main results. That is, if we use, here we are, let's say we use different dynamics to explore a landscape like this, that has, as we can see, two sharper regions and two wider, flatter regions. So first, if the dynamics is driven by heavy tone, and the histogram shows the proportion of time we spend around different locations over the landscape. So if we use a heavy tail dynamics to explore a landscape, but without clipping, what we can see here is, so we still spend some time around the sharper region. Once we start adding gradient clipping, these time are almost completely gone. So this is of course, if we believe with a flat minima full course, this does seem to benefit. Yeah, so as I said, this is a sort of a trailer of our main results. And now we see what's going to happen on the truncated heavy tone noise. The main goal afterwards is to understand why we have this phenomenon. And more importantly, just from this figure, it may seem like maybe what truncated heavy tone noise does is it just makes you stuck at a flatter region and at a flat region, and you never leave it. We're going to show you what's happening in practice. You are still exploring the entire loss landscape. So you are still visiting different places, but also manage to almost always stay at the flatter region. So we'll part of the goal of the talk is trying to show this phenomenon. And after we understand this phenomenon, we'll show that how this insight can help us achieve better test performance in deep learning by incorporating heavy tone noise in the right. So yeah, this is sort of an overview of the talk. And there are three main components in this talk. First, we understand the main technical tool, that is heavy tail large deviations. Once we have that, we use it, apply it to understand the global dynamics of heavy tail SGD, and then we translate these insights into the benefits in deep learning experiments. All right, we start from, yes.
So just to understand, in your simulation, you're not just sampling from the gradients, you're injecting additional noise in addition to the
subsample. We'll be adding heavy tail noise in this one. So in some sense, it's like you have some control over what noises you have in the experiments.
But then for the actual gradient, you're taking the full gradient, or you're sampling from the...
It's still from the subset. Yeah. So it's still a stochastic gradient. Yeah, I will dive into details, but let me know if it's still not clear when we are at that section. But thanks for the question. All right, this is the outline. Let's start from the first section. So I will start by talking about for the audience in this room, I believe this is an obvious fact, but let me make it brief. So there is a key difference between a light tail and heavy tail system. That is, there's a fundamental difference in terms of how the rare events are going to happen in these different systems. very briefly speaking, in the light-tail cases, such as say human height distribution is a light-tail one. This is a photo of the tallest person known in history. Just from this photo, what we can learn is he is indeed very tall, but also no one has been twice as tall as average human being. So this is a common phenomenon in light-tail distribution, that is extreme values are not that often. In the heavy-tail case, so we are considering a situation where extreme values become much more often. For instance, if you instead look at any social media platform, then a celebrity or influencer, they're gonna easily have thousands or hundreds of thousands times more followers when compared to an average user. So this is an obvious fact that this is a manifestation of the phenomenon that extreme values are more often under heavy-tail noise. Of course, there are heavy-tail distributions. Of course, there are a lot of stereotypical heavy-tail distributions, such as power law, Weibull, and law of normal. This talk, we focus on the regular variant type. In other words, the power law type. And yeah, the precise definition is just that the tail CDF decays at a polynomial rate multiplied by some slowly varying functions. But I think for easier presentation of most of the results, I mean, obviously the key part is polynomial term. And for most results I'll be presenting here, it will be a slightly informal form. That is, I will skip the slowly varying part. But yeah, in some sense, we can just, in some sense, the results are precise in a setting where they're exact power law. But I mean, I think I just want to mention this. Right. All right. So the reason that we're so the interesting difference between the two settings is beyond the fact that extreme values are more often in heavy-tail under heavy-tail distributions. More importantly, there is a structural difference in how rare events going to happen in different systems. In other words, how the system will actually go wrong. In the light-tail case, we will observe this so-called conspiracy principle. That is, when the system goes wrong and when rare events arise in the system, it's almost always because every single component goes wrong a little bit. Whereas in the heavy-tail case, we observe the catastrophe principle, the so-called catastrophe principle, which is a generalization of the one large jump principle. That is, when the system goes wrong, it's actually most of the components are behaving normally. Just a few of them go wrong, but they go horribly wrong. So their effects alone would drive the system to deviate significantly from their typical behavior. And again, for the audience in this room, I think this requires no introduction. But just to make things more precise, we will return to our running example, that is the SGD context, especially how SGD explores the landscape. So to understand the rare events or the atypical behavior, we start from the typical behavior of SGD. Again, F is a training loss function. Eta is the learning rate parameter. Suppose this is how F looks. What I'm trying to do here is, suppose this is where we start. And in the next few iterates, this is how we move along the loss landscape. What I'm trying to do here is I'm trying to visualize the trajectory of SGD. In other words, how the location of SGD changes as time evolves. And here, I mean, I think it's intuitive, but just let me explain. So I rotate this by 90 degrees. Now I consider the horizontal axis as the time axis. Then at different time t, I'm plotting the location of SGD in the sense that if you compare it against the loss landscape shown on the left, you will know the location you are at that timestamp. So this is what I meant by showing visualizing the trajectory of SGD. So I hope at least this part is like what's the meaning of the figure. Okay, cool, yeah. So now for given eta, let's try to visualize the trajectory up until timestamp 1 over eta. As eta decreases, so of course, at the beginning, you may see more chaotic patterns. As eta decreases, it starts to become apparent that they're almost always following the same path. That is the gradient flow path. And gradient flow here is just the corresponding ODE. The ODE is starting from the corresponding initial value. And also, depending on where you actually start, you may start from different so-called attraction fields. In the sense that the gradient flow path will be attracted back to different local minima. Okay, this is depending on the initial value. But what's worth mentioning here, which again is obvious for the audience here, but what's worth mentioning here is that this is a law of large number type of results, meaning that this is what you would typically see, regardless of whether this is driven by heavy tail or light tail noise, as long as the so-called noise does have, say, 0 mean. And again, this is obvious, but let's confirm this through some simulation experiments. Here I'm comparing the trajectory of SGD driven by light tail noise against trajectory of SGD driven by heavy tail noise. As step length decreases, we start to see, not surprising, but they follow the same pattern, that is, both are following the gradient flow path and they are being attracted back to local minima. And of course, this is expected. What we learn from this is that it's gonna be, in most cases, you will just be attracted back to local minima. So the scenarios where you say deviate from the path, or say, let's say cross the boundary and start exploring the other half of the domain, this is not what's gonna happen very often. In other words, when we're asking this question about how SGD escapes the explores the loss landscape, especially how it escapes the local minima on this relatively small learning rates, we are basically asking how these ray events are going to happen in a heavy tail system. And now let's see how these how the exit would happen. We ask the question of what are the possibilities, what are the possible ways for exit? There are infinitely many possible ways, and here I'm just showing a few of them. They're all possible scenarios. The question is, what's the more likely ones, or if there actually exist the most likely ones? But and also we know this is a typical behavior. So if we instead ask the question of how many perturbations I actually need to apply to the typical behavior for us to exit, the answer is you actually just need one jump, right? As long as the direction of the jump is pointing towards the right direction, and the size is large enough, you can always escape with just one jump. The key result here is that if one jump pass, they're actually the most likely scenario for us to escape under heavy tail noise. Here's what I mean. So there's more simulation experiments, again, comparing light tail and heavy tail cases. But the key difference here is now the results are conditionally on the exit. In other words, I'm only showing the path if the path actually cross the boundary. Yes.
So one question. So your analysis of this typical path kind of relies on sending the learning rate to 0, right?
Yes.
But in reality, you would actually choose the learning rate as large as still possible while obtaining convergence. So.
Let me see if I get the question correct. So the theoretical results, as you said, will be of the nature will be asymptotic. Are you asking, say, how small it needs to be for the results to show up, or is there is that the question?
So kind of if it represents the actual behavior you're going to see of stochastic gradient descent in applications, because you will have a larger learning rate, you will still see lots of fluctuations.
Yeah, good question. So this is more, I think the goal of this, maybe let me make this part clear. So if it's a bit confusing, I apologize for that. Here I'm trying to introduce a tool about, say, heavy tail large deviation. So I'm showing that up until, say, time 1/8, this will be rare. But the point in the second section is, with this tool, you understand the typical behavior. So typically, how long it takes for it to exit. So yeah, I hope when we are there, we'll be clear. But this is rare because I didn't show the time scale here, but it's up until 1/8. So it's within the law of large number type of scaling regime here. When we look at the longer time horizon, we will escape eventually. And the key here is using this piece of knowledge about the rare events on this not too long time horizon. You can repeatedly applying this knowledge to understand how we behave under a much longer time horizon, and typically how long it takes for us to exit. So yeah, I hope it's gonna be clear when we are at that part. All right, so this is we simulate the path up until time 1/8. We compare it's conditionally on the exit, and now let's see what's the difference. So as the step length decreases this time, there's a clear difference. So like that, you can see that it's almost as if we're doing gradient ascent. So we're actually making exit. It's as if we're doing gradient ascent and always climbing up the hill. In the Havidale case, it's just like the one jump path we have seen earlier. So most of the time you are behaving normally, but up until a certain point, there's just a super large noise that sends you outside of the deviations in one jump. This is, I believe this is already very interesting because things will also get more involved when we remember that we will be adding gradient curve. Again, phi will be the clipping operator. B is a clipping threshold. What it does is that now under this clipping regime, this is how far you'll be traveling within one step. So B confines our movement within one iteration. Let's say B is so chosen that now now we cannot escape with just one jump because we're confined with that region. And let's say we need at least 2 jumps to escape. So under this choice of B, we need at least 2 jumps to escape. That's what I mean. And of course, when you're choosing different B, or if the landscape is even, if we're considering a different landscape in the sense that it's actually wider, we can see that we'll have cases that we need, let's say, 3 jumps, 4 jumps, or even more jumps for us to escape. So there is a key quantity that is R is the actual distance you need to travel in order to exit if you start from a local minimum. B is a clipping threshold. There is an important quantity that's so-called relative width, which is a number, which the definition is the ratio between R and B, rounded up to an integer. The actual meaning is just the number of jumps required for the escape from this attraction field. Yeah. So what we will see here, what we will see next is that this relative width metric, they're going to play this relative width quantity metric is not the precise term. Quantity, they're going to play a role in determining how we're going to exit from the local minima. So again, some simulation experiment. This time I'm adding gradient clipping. As step length decreases, we start to see 2 distinct patterns again. In the Lytle case, we see the conspiracy principle. That is, when Lytle SGD goes wrong, it's almost because everything goes wrong a little bit, and at any given moment, we are always fighting against the attraction. In the Havidale case, we observe this is a manifestation of the catastrophe principle. That is, most of the time it's behaving normally. A few components, in this case, the number is exactly 2. A few components go horribly wrong, and their effect alone would drive us to deviate significantly from the typical behavior, even though most of the time you're just behaving normally. And I hope the visualization or the demonstration so far is clear. And so far we've been focusing on this very specific case about how Havidale SGD escapes from attraction field within a certain time scale. But this phenomenon actually extends to far more general settings. Here we present the results. So let's use bold X to denote the sample path up until time 1 over eta. And just recall that we're considering the Havidale case in the sense that the perturbations are following regularly varying laws. Here enters the main results, and the gist is that given any rare event, there is a key quantity JA that first, it determines the polynomial decay rate of the probability of these sequence of rare events. In other words, it tells you how rare these events are. But equally importantly, it also determines what's the most likely scenario for the rare event to happen. So the conditioning on the event actually happens. The conditional law would converge to the law of, this is a informal description, but broadly speaking, it's converging to the law of the ODEs perturbed by several random jumps. So the exact number of the random jumps, again, is equal to JX. So there's an important quantity. And this is a more formal version of the result, which will be nice. So we actually have a control over the leading coefficient. Here is just the interior and the closure of the setting. There will be a measure that I'm not showing you the exact expression or of the measure, but you can write down the exact expression. For the purpose of this talk, I will not be using the leading coefficient, so I'm not introducing it. But you can have the explicit expression. So first, I think you guys can see that this is a Havidale version of friendly width theorem, and in the meantime, it's an extension of Changhan, Hossein, and Burr's work. Bert's work on the sample path log deviation for habitable Levy process and random walks. So now the increments are not purely IED; they have some spatial and temporal dependence. But it's basically the generalization of the one large jump principle to multiple jump cases, and the generalization from the IED increment settings. Should I introduce it? Oh, okay. So I said there's an important quantity. So the definition is just the smallest number of jumps required to trigger the reverse. Okay. And just to quickly mention, so far we've been focusing on this specific form of SGD. The results applies to more general settings. For instance, you can add a diffusion coefficient, and also it applies to the continuous time SDE driven by Levy process with regularly varying increments. So just to say that this, of course, applies to other types of dynamical systems listed here. And also the stochastic difference equation with general drift and diffusion coefficient. So yeah, this is habitable large deviations. That will be the fundamental tool for us to understand the global dynamics. And now we have seen this tool. Let's see how we apply this to understand the global behavior of habitable SGD. Again, let's do a quick recap of what I'm trying to understand. This is the figure I've shown at the beginning. We have seen that without gradient clipping, you spend some time around sharp region. Once you do gradient clipping, these time are almost completely gone. This is the phenomenon I'm trying to understand. First, we have this rigorous characterization of the phenomenon. That is, there will be some index beta, which basically implicates say how long you want to run your training. Suppose you run it long enough, then this equation, so the result here on the left-hand side is the proportion of time the SGD will spend around the so-called narrow regions. As the step length eta decreases, the proportion of time you spend around narrow regions, they converge to 0. So for the interpretation of the result in the training is that you don't really need to worry too much about, I guess, other things. Once you know that, I mean, it's unclear whether you know it or not, but if you know that you're training this for long enough, just make sure that as long as the step length eta is small enough, this asymptotics will take care of things and provides it almost always guarantee that you are at the so-called narrow region at the so-called wider regions. And we'll make this definition precise, but this is a rigorous characterization of the phenomenon. But in fact, a lot more can be said about the actual behavior along the entire sample. So this is what we showed, that is under this scaling using beta again, this beta order scaling again for the time scale. The path of SGD, habitable SGD converges to a Markov chain that only visits the widest. Here is what it means. So again, this is basically another version of this figure, but now we're showing one of the sample paths. Yeah. All right. In the case we're not doing clipping, you can see that we're constantly hopping around different regions. Once we start adding gradient clipping, it looks like a Markov chain that only jumps between the widest regions. So this is what the result means. In other words, this phenomenon of almost always staying at the wide minima, we have a rigorous characterization, but what's important here is it doesn't mean that you're just stuck at the widest region. You're actually still jumping, but you behave in a way that it behaves in a way that's similar to a CTMC that only visits the widest minimum. So yeah, this is a phenomena we're trying to understand. Just to quickly mention, this convergence is in terms of finite dimension distribution and under LP topology. All right, so to understand why we behave this way, the key question is how much time you're actually spending at different regions. So the key here will be we're trying to understand the time it takes. Again, the time it takes for us to say the time we'll be spending in a attraction field. Let's use omega denote attraction field associated with the local minimum M. R is again the so-called actual radius, that is the actual distance you need to travel for exit. First exit time tau is the number of steps it requires for you to exit. We have seen first exit time analysis already in the week, so I'm sure you guys know what I mean here. This relative width notion we have, this relative width quantity, we have seen it already. It's the number of jumps required for escape. It's a ratio between R and the clipping threshold B. For instance, here I'm showing a case that if B is so chosen, then L will be equal to 3. You need 3 jumps to escape under this truncation regime. And L does play an important role in determining the exit time. So there will be a scale function gamma. Here the index is alpha is just the power index for gradient noise. In other words, you can say that it's determined by L, so relatively. This scale, under this scaling, first exit time converges to a exponential random variable as eta decreases. The takeaway is that now we know the order of tau when eta is small. So this is basically 1 over gamma will be the order. This is the order of the first exit time. It's determined not by R directly, but instead L. Meaning that the wider the minima is, of course, relative to the clipping threshold, the much longer time you're spending around this. Now we have this, you can, and of course, it's a habitable version of the Eyring-Kramers theorem. Now we have this, we can understand the, let's zoom out a bit from just one local minimum and understand the global behavior. Let's say they're under certain clipping regime, under certain choice of B. For the left, most and right, most region, you can still escape with 1 jump. For the one in the middle, you need, let's say, L jumps to escape. Then applying our results, all these terms shows the rough order of the exit time under the current truncation threshold. And let's say even if the basin in the middle is just barely larger than the other ones, meaning that let's say L is just equal to 2, so it's barely larger than the other ones, still what you will see is that the term in the middle, in other words, the time you spend around the wider regions compared to the other regions, as eta decreases, they're going to grow at a much faster rate because they have a large index. Meaning that as eta decreases, they grow much faster to the point that eventually they are going to dominate the entire timeline. And the time you spend at any other region is almost negligible, just because it has a higher index. So this is how this so-called you spend much longer time at a wider region manifests at a global level. And of course, it's easy to see that now we're just looking at three attraction fields. It's easy to see that it's natural to see that this can be extended to the point that you spend almost all time at the widest regions.
So you scale your x eta, right? Or x eta converges to this Markov chain that sort of visits this. And here you're somehow describing the stationary measure of that Markov chain. And you
this is this is the exit time. So it's the time it takes for it to leave.
Okay, so it's not exactly. It's not.
Yeah. So far, I think throughout the talk there will be no results about stash.
So essentially, in this case, you may have convergence to the Poisson process. Essentially, is something like that. Yeah.
Yeah. Actually, yes. Yeah. So
well,
that's
you have to have this. You have this functional limit theorem. Yes, essentially. But when you arrive in the orange area, you just see some points. You know, you have to have Poisson. So you have to have some memberless property and have convergence not only marginal but functional. You have to have it's better to formulate in terms of functional limit theorem.
Yeah, I think actually yes. So that's why it eventually converges to a Markov chain because
in terms of
so first you almost all first the time you spend around widest region almost always our timeline, right? And also the soldier time at any region. It's almost memoryless in the then it pretty much just screams that there is a Markov chain because the holding time that once you return to local minima, it's memoryless in some sense, and you're almost always staying at the widest.
So I think it's most likely in Skorokhod topology you have this convergence, this Skorokhod topology.
Oh, you mean there's a
as process here.
Oh, yeah. So we show this in terms of the other LP.
Yeah, much marginal, yeah, but you can do it in terms of processes.
Oh yeah, we do it for yeah. Right now we show this on the LP. It's at the path level.
So yesterday,
Yes.
there was a mention of this paper by Pavlyukovich on metastability for stable-driven SDEs, which also proved convergence of two continuous time Markov chain. So I was wondering if you're using kind of those ideas in your work.
So I guess it's slightly different. So maybe in the remaining 5 minutes, I will just quickly go how it's obtained. Maybe I'll skip the experiment part, but just feel free to let me know if you're interested in the part. I'm more than happy to discuss offline.
Sorry, another thing, to make this difference in regimes more stark, you should choose alpha very close to 2, right?
Oh, good point. So
heavy tail, but not.
yeah, we didn't fine tune this parameter, mostly in the experiments, mostly because we don't have that resource, but
No, I understand this, but I mean.
I think if alpha is too small, it's gonna happen relatively slowly. So the training, like basically for you to see this phenomenon, let's say we have this ergodic people here, right? So you need to train this over say 1/beta order of time. Beta will basically be L, which is the widest, the largest L times alpha. So if alpha is too large, then that means you need to train very long for you to see the field. So alpha, if alpha is
So that's too large? So too close to 2 or too?
Also, in our case, alpha can actually be larger than 2 because we're just considering regularly varying parts, not necessarily say alpha stable. So you can actually have alpha larger than, I mean, that's what I mean. Like if alpha is too large, then it's basically like 2.
Okay.
Yeah.
Oh, sorry.
In our case, we do want to have, say, at least infinite variance to see if that is faster, but at least we want this to be.
Sure.
For this reason, the whole bottom line is alpha should be at least have a finite mean.
Sure.
Yeah, but but we happen to choose a value that's not too close to 2. Yeah. So that's why. Oh, sure. Yeah. So let me finish this by quickly mentioning why we can use large deviations to obtain these results. So there's a theoretical framework mostly captured in the following paper. Yeah. What we have learned is so over a relatively short time period, this is how things will go wrong. That's through several large jumps. We know how often it happens as well, using the asymptotics in the result, in the large deviation result. Also, we know the typical behavior. So now let's zoom out a bit and look at the longer time horizon. What these knowledge can help us to do is that now you can just consider this. You can divide the time horizon into several short cycles. Over each short cycle, you know how likely you can successfully escape. In a sense, you know how many attempts you need to make and how long you need to wait for it to successfully escape. So this is how we go from large deviation to the X time analysis. Once you're at a different place, you can just repeat this analysis. Say now that we're at a different place, so I want to know how long I need to wait again for us to move to a different place again by dividing this into small cycles. By zooming out further and further and repeating this structure of analysis, we will eventually get a clear sense of how we are moving global. This is how we move from the exit time analysis to understanding the global dynamics. It's probably already obvious from the animation. The key argument here that glues everything is that whenever you return to the local minimum, no matter which one it is, the process pretty much regenerates, almost regenerates. This almost regeneration is just as intuitive as it sounds. So starting exactly from local minimum, we have a good understanding of how we're going to behave. Are we going to exactly hit local minimum ever throughout the training? Probably not. But even if we just return to a small neighborhood, we have a pretty good understanding of the behavior. And the understanding will be more and more precise if you look at a smaller and smaller region. So yeah, basically we capture, it can be somewhat generalized to a notion of asymptotic atom. Whereas once you return to this region, the process almost regenerates in the sense that what's going to happen afterwards is almost the same. And are we going to have the exact regeneration? Probably not, but do we need exact regeneration to obtain this result? I don't think so. So this is a key message from the development of the asymptotic atom. And yeah, it requires a slightly stronger version of the catastrophe principle, but it just means that now I'm considering the initial value. So yeah, so actually that's it. Yeah, this is the end of the. Yeah.